Hello, welcome to the ESA-Lab@CH IGLUNA project livestream. This project is coordinated by the Swiss Space Center and supported by the European Space Agency and the Swiss government. My name is Gilles Feusier and I'm working with the Swiss Space Center. Now, I'm very pleased to introduce you the IGLUNA 2020 Project Team 6 Hydration. This team is a very international team led by the MIT, the Massachusetts Institute of Technology in Boston, USA, including students from EPFL in Switzerland as well. What makes this team so special for me that outside of being of a very high level of expertise, it's quite large and composed of people from all around the world. Today, the team will present its very interesting and relevant project during about 30 minutes and will then answer to your questions until the end of the session, which means that we will end at 4:30 p.m. Swiss time at the latest. For asking your questions, please use YouTube chat. I will then forward them to the team. You can, of course, use the chat during Team 6 presentation. I'm sure you will be very interested by Team Hydration's talk, Digging into the Moon and Mars for Water. Hello, George. How are you doing? I give you and your team the word to describe now your exciting project.
Thank you, Gilles. Thank you very much. Can we survive on the frozen, nearly airless desert of the planet Mars? Not without water. I am George Lotus, PhD candidate with MIT's Engineering Systems Lab, working on sustainable habitation for the Moon and Mars, and the team lead of the Hydration 2 project. Our team is developing an engineering prototype of a remotely operated water exploration and production system to search for ice at the lunar South Pole and to produce water from buried ice sheets on Mars. 50 years ago, Apollo spacecraft carried all the water needed by the crew on their journeys to the Moon. These days, ESA, NASA, and others are planning for humans to explore more sustainably by using the resources that we can find on the Moon and Mars, a strategy known as In-situ Resource Utilization. The good news is that ESA and NASA spacecraft orbiting our Moon and the Red Planet have recently detected signs of substantial amounts of water ice just under the surface. About 10 years ago, the Lunar Reconnaissance Orbiter satellite found hints of water ice near the lunar South Pole by counting neutrons and by spotting water vapor in a plume created by the deliberate impact of an empty rocket stage inside the permanently shadowed Mars crater. Water ice just under the surface. In 2018, as a NASA satellite orbiting Mars observed partially exposed sheets of water ice covered by very shallow layers of dirt, as you can see in the picture on the right. We can build bases and even live there. But first, we need new machines to find and access this water. In response, our team is developing a prototype system for finding and producing fresh water from buried ice on the Moon and Mars. Let's watch a short video to see how this will work.
Here is a drawing of our Hydration 2 prototype. Hydration stands for High Yield Dihydrogen-monoxide Recovery and Terrain Identification on your words. The drill bit is off the shelf and optimized for concrete. A heater with a water pickup pipe is lowered in the hole and the pump collects the water. At this stage, hydration is a proof of concept to test all the mechanical and electrical controls and sensors that allow the onboard computers to safely control the drilling, melting, and water pumping, while an astronaut back at base directs operations remotely via a laptop. Here is hydration in action. The drilling strategy is to control the vertical speed using stepper motors and a lead screw. The drilling mud stabilizes the hole, and if we hit a rock, the drill uses hammering action to break through. The drill bit is removed from the hole, leaving an open path down to the ice. The Y-axis motor moves the heater a fixed distance directly over the hole, and another motor lowers the heater into the hole in the ice, and we start melting and pumping for about 20 minutes. A cavity is melted into the ice, and the water is pumped up through this silicone tube. And here is some water we collected during a test at MIT.
Our project began at MIT in 2017 as Hydra, and continued in 2018 with the invention of the hydration concept, both with support from NASA and the United States National Institute of Aerospace. Our expanded team went international in 2019 with students from MIT, EPFL, and the University of Tokyo, and with additional support from the Swiss Space Center, for which we're grateful. We have diverse interests, backgrounds, and experiences, and this diversity is mirrored in the several capabilities we are building into our project. In the rest of this presentation, you will see and hear the story of some of our team members who have been building hydration tools for the last year. I would now like to introduce you to my colleague, Paula, an MIT student from Brazil.
Thank you, George. As George mentioned, our main goal is to drill through regolith and extract the subsurface ice through melting. To be able to accomplish that goal, there are 4 main subsystems in hydration 2: the drilling assembly, the water collection assembly, the supporting structure, and the supporting sensors and electronics. All 4 subsystems are integrated in a standalone assembly, as can be seen in the picture in this slide. The drilling assembly is composed mainly by the drill, which brings the power and torque to break through the soil, the drill bit, which cuts through the soil, the auger, which brings the chips out of the hole, the lead screw, which guides the drill downwards to promote penetration, the stepper motor, which turns the lead screw, and 4 sensors that measure how hard the drill is pushing through the soil and how hard the soil is fighting back. And they are the torque on bit, the weight on bit, the drill bit rate of rotation, and vibration. The water collection assembly is composed by a set of cartridge heaters, which melt the ice, a thermocouple, which measures how hot the heaters are, a rate of penetration sensor, tubing, and a peristaltic pump to collect the meltwater. And, just like the drilling assembly, a set of lead screw and stepper motor to guide the heaters inside the hole. The supporting structure has other 2 sets of lead screws and stepper motors to move the drilling and water collection assemblies front and back and side to side. The supporting structure also hosts the electronic and electric panel, where the drilling current and power and sound are measured, the data is processed, and the software that controls the entire system runs. The mechanical components we use in hydration 2 are robust and of common and traditional use. This decreases the implementation risk of hydration 2 and facilitates the future path to flight. The 4 translational degrees of freedom are actuated by a stepper motor each, as the one you can see in the image on the left, and are guided by lead screws and supported by linear bearings, as the ones you can see in the left center of this slide. The drill is an off-the-shelf product from Bosch, as the one you can see in the center right picture. Lastly, we use computer-aided design to model and simulate our components before building the system to ensure the dimensions and interfaces are correct. The image on the right is a computer rendering of Hydration 2 CAD. One important aspect of hydration's concept of operation is that the walls of the drilled hole don't collapse between the moment we remove the drill and the moment we insert the heaters. To understand how this works, let's watch this video. The first step is using a concrete drill bit to drill through the soil and overburden. After a certain depth, the drill will reach the ice and the friction will melt a little amount of ice. This meltwater will mix with the chips and soil debris and produce the mud that you see on this video. This mud will create a light structural layer of homogeneous material on the walls of the drilled hole, preventing looser layers of soil, like sand, from falling into the hole. We are then able to remove the drill bit and insert the heaters through the hole and into the ice below it. And now, to talk about the drill, please welcome our next speaker, Roland, an MIT student from the United States.
Thank you. Our goals with this were to create a simple system using standard off-the-shelf parts where we could, and that parts that were readily available. The nice thing is most of the pieces that we have here, with the exception of the adapter, which I'll explain in a moment, can be bought at a local home shop or hardware store. The adapter is a unique piece that we had to create. We're using a medium-duty drill, and we're using a heavy-duty bit to go into the hole. The reason we need the heavy-duty bit is because of the size and the depth of the hole. We're using the medium-duty drill to keep weight down in the rig and also for lower power consumption. So the piece outlined in red is actually an adapter that we fabricated using another drill for parts, a drill bit, so that we had the correct sleeve to fit into the drill. And the one custom piece we had to make was a simple cylinder that we welded into the middle. And this allows for the adaptation between the larger bit and the smaller drill. In the past, we used a 3-jaw chuck, which in service did not perform well. And so that's why we've gone this route. The other piece that we have been custom developing is the heater. And the heater has taken on 2 forms. The heater, which we'll see in a moment, the original heater on the far left was a single cartridge design. The cartridge is also an off-the-shelf piece. The water pickup shown next to that in the far left, the smaller pipe, is a standard automotive repair part. It's a brake line, and a copper pipe was used to crimp the 2 together. The middle left picture is the unit in service on the rig having been lowered into a hole. You can see it's somewhat coated in mud, which is typical. We're designing a new heater with 6 of these elements instead of 1. The main reason is that the brake line casts a shadow when we're melting the ice, and we lose efficiency with that. The heater is designed to be radiative only, so the heater actually stays above water when we melt it, and the radiant heat melts the ice, which we then pump up. In the middle right picture, you can see the heater elements that we're using and a CAD-based design for that. And on the far right, you can see the analysis that we're doing with CAD systems to see the heat output on this system. The one thing that we have to talk about, I'll talk about now, is how we actually get the water out of the hole once we've melted it. We use a pump, and we have a filter on that pump. The filter is pictured on the left. The requirements that we were looking for was that the pump has to be self-priming. And at the same time, we need to remove any objects larger than 200 microns. The heaters have to remain above the water, otherwise they lose efficiency. And the other thing that we needed from our pump was to be able to do in-place cleaning, and the whole system needs to be sturdy. Otherwise, as we're lowering down the hole, if there's a collapse of the hole or a rock or something in the way, we can't have the filter getting crushed. So we use a peristaltic pump because it can run in both directions and it's positive displacement. So it will self-prime, and it will also provide reasonable pressure to backflush the filter. We have an open brass filter construction, open cell brass, filter for stability and sturdiness. It's mounted below the heaters so that we can keep the heaters above the water line. And then we have the steel collection tube that allows the stability of the filter. This whole system works well. It was tested in place last year at NASA Langley and performed nicely. Let me now please introduce Marcelin from France and a member of the EPFL team who will talk about some of the instrumentation on this rig.
Thank you, Roland. To compute the rotation speed of the drill, we use a sensor called a tachometer. This is an instrument that measures the rotation speed of a machine, usually in rotations per minute, or RPM. There exist different types of tachometer, the 3 main being magnetic, mechanical, and optical. We chose the latter because of its accuracy and robustness. The physical principle behind it is pretty simple. An infrared light source is pointed on the rotating device onto which a reflective material is attached. At each revolution, the beam is reflected on a detector located next to the infrared emitter, which is then transmitted as an electrical pulse. Using the number of revolutions during a certain amount of time, we can deduce the number of RPM. The brain of the sensor is a simple microcontroller, or in simpler words, a small computer. The variations of the rotation speed of the drill when digging can enable to get informations on the soil, especially what it is composed of. Another parameter that can give useful information on the soil is the acceleration experienced by the drill. The vibrations will depend on the type of rock or dirt that is being dug. To compute those vibrations, we use an inertial measurement unit, or IMU. Composed of accelerometers and gyroscopes, the type of electronic device measures linear accelerations and rotational rates. IMUs are typically used to maneuver aircraft and spacecraft. The one that equips Hydration 2 can measure acceleration of up to 16 times the gravitational acceleration on Earth, or 16 Gs. The IMU is embedded on the microcontroller used for the tachometer. By combining the variation of rotation speed of the drill and the vibrations experienced and sending them to the machine learning algorithm, we can obtain information on the different layers that we are digging through. A famous example is the lunar regolith, but many other types of rocks and dirts will be encountered too. For future crewed flights, especially on Mars, In-situ Resource Utilization, or ISRU, will be vital. However, the extreme conditions encountered on other celestial bodies make this endeavor really hard. To solve this issue, a remote operation of Hydration 2 seems to be a safe and reliable option for the astronauts from the base. In this case, they will only have to go out to pick up the water. And last but not least, it happens to be one of the themes of IGLUNA 2020, since, as stated, the purpose of the mission is to demonstrate technologies for a space habitat that will sustain life in an extreme environment and to operate the novel technologies through a remote control mode. Now I'm going to let Shunishiro talk, a University of Tokyo student from Japan.
Thank you. This diagram shows the software architecture. Hydration 2 has a small computer called Raspberry Pi, where the main software is running. The Raspberry Pi receives the measurement data from the sensors, computes what to do based on the current operation mode, and controls the actuators. To simulate the actual operation environment, we access the Raspberry Pi through the internet and remotely control the system. This diagram shows the sequence of operation. There are 4 operation modes. Initialize operation, where we start up the system. Position operation, where we position the drill. Drill operation, where we drill a hole. And melt extract operation, where we lower the heater into the hole and melt and extract water. In each mode, the software controls the system with a different policy, and once the operation in that mode is done, the operator sends the command to the system, and the system transits to another mode. Now I'll hand over to Chloe, an EPFL student from France.
Thank you. How was it working on hydration during this very special year? Here is a short video of the EPFL team behind the scenes of a few hydration sensors. Let's take a look. Hey everyone, welcome on board our trip to the Moon and Mars. We are the EPFL team, part of Hydration 2, and we worked on 2 sensors to be integrated on the hydration machine, a tachometer and an accelerometer.
In the frame of the hydration experiment, the tachometer aims to differentiate between different layers of the ground and to identify the ice layers which will be extracted later on by the rest of the machinery. Simply put, a tachometer is a measuring device for the rotation speed of a shaft or a disc.
challenge for me was to build something.
Because we were a group of 4 students with a background in physics, and although we had bases in electronics, programming, etc., it was, at least for me, the first time I was building and designing an engineered device.
But we figured it out.
Okay, this is Chloe from Switzerland for test 1A in concrete.
And from the beginning, we've been warmly welcomed within the MIT team, and it has been a great experience to work alongside all of these brilliant and really nice people from all over the world.
I'm confident about the reliability and the accuracy of the system we built, and hope to find the whole hydration device within extraplanetary missions in a few years.
So now you know exactly how we plan on extracting water on the moon or Mars. What is the next step? Sending it to the moon, maybe? We definitely don't want to send it up there without testing it first. And this is when analog missions come into play. We fail on Earth so we can succeed on the moon. This is why our team is part of IGLUNA, a test bed in extreme conditions, and the Swiss analog mission Asclepios to take place in February 2021. Analog missions simulate life on other planets in remote locations on Earth. They put analog astronauts, selected and trained, in isolation to perform experiments useful for the future of space exploration. In Switzerland, we are very lucky because we have the chance of having the Alps right next by with a lot of tunnels, which makes it perfect to testing our device. These opportunities allow us to collect lessons learned and improve our technology until it is space qualified. But at last, our final objective is to make it to the moon or Mars. A few missions are planned by several agencies such as the NASA Artemis program and private companies like SpaceX. We are hoping to get a place on the first Starship that we go to the moon. Look for hydration in a few years on the moon's surface.
So thank you, Hydration, for this great presentation. I'm really impressed with what you are doing, and I'm looking forward to seeing your project flying to the moon or Mars. Dear listeners, do not hesitate to continue to post your questions on the YouTube chat as well. I have now a first question to the Hydration team. Would your drill work as well in partial gravity, and would the gravity level change its efficiency?
So the drill system would work also in partial gravity. The changes that we would want to make to adapt to the environment of the moon or Mars will be driven more by other factors, such as the lack of an atmosphere, complete lack of atmosphere on the moon, and very little atmosphere on Mars, and also the temperature changes in the thermal environment. So the main change that we would have to make from this engineering prototype to create a flight article would be to replace the liquid water extraction with an extraction of vapors using a scroll compressor that collects sublimated vapors from the hole and either freezes them or collects them as liquid water. But the gravity would not make a big difference to the design.
Okay, thank you very much. And I have a second question. Beside IGLUNA, what other competition will you plan to participate in? What are the next steps for you?
I can take that one. So besides the IGLUNA, we are also participating on a competition that is similar in the United States. It's from NASA and it's called Rascal Special Edition, Moon to Mars Ice and Prospecting Challenge. And it was supposed to happen in this 2020 year as well, but it was pushed to 2021 because of coronavirus. And besides that other competition, we are also writing a technical paper to the Ascend conference that is going to happen in the fall. And after that, we plan to keep improving our system and have a clear path to flight.
Thank you very much. Another question, more technical. With the current status of your system, how many liters per hour can you produce?
I can take that one. Thank you. We actually have in-competition experience with this from doing the NASA competition last year. And in last year's competition, we produced about 5.5 liters of water over 9 hours of competition time. This comes out to be about 0.6 liters per hour. I have to say, having been there, most of that 9 hours was spent managing contingency conditions that we've spent a lot of time this year working on. The drill adapter was one of them. Unfortunately, we lost a power supply, which is why we only did 9 of the 12 hours. But I think we have the capability of generating a lot more water than that. We're looking at a newer high-quality industrial strength power supply and some other equipment to bring the rig up to higher reliability. But I anticipate doing much better this year. We did get first water last year when we ran it.
I maybe jump. I see another question related and asking, would there be any efficiency problem regarding pumping in the water in space environment, low gravity, temperature?
I can take that question. So we don't plan to actually use pumping on a flight article. We don't expect liquid water to persist for long. So the idea is that we will have what is called a packer, which will expand and seal the hole above the ice. And then the heater will cause water vapors to appear. And these will be collected by the pressure differential caused by a scroll compressor at the surface. We will have holes above in the pickup tube along the sides. And we feel that this system will actually have less complexity and less risk, less operational risk, because you don't have to deal with filtering and backwashing and cleaning filters. You are just collecting vapors. So, but there is a lot of testing still to do because the vapors can entrain particulates as well. So there is work to do.
Okay, thank you very much. Another question related to how do you fix the drill in the moon surface? Do you have to fix it?
So the drill that we acquired, which is a standard construction, it both hammers and drills. I would assume that for actual use on the moon, because that drill is air cooled, there would be something specific developed for Moon or Mars that would not require air cooling. The drill itself needs to be made reliable. There isn't going to be somebody out there to tinker with it, to tighten it, to wrap electrical tape around the chuck when it fails. So there is no sort of in-field repair. If you were in the middle of drilling, you would have to stop drilling and bring the rig back. The rig is designed to be mounted on a rover or some other machine that could autonomously or with a driver move around the surface. But there is no expectation of a in-service repair.
Another question related to the location of our system. For which celestial bodies is it done for? So I heard for Moon and Mars. Is there any other Earth applications?
I wouldn't say so. No, I wouldn't say that there is an Earth application. It's very specific to the expected conditions on the Moon and Mars, where you have ice that is buried at the shallow level under the regolith. And that's the only water that's available, so you get that water. The way we collect water on Earth is so much easier in comparison, so you wouldn't have an Earth application.
Okay, I have now a question related to the participation. Did participating in IGLUNA started new collaboration between MIT and EPFL or other European entities?
Maybe I can answer part of it. So I'm Chloe, I'm from EPFL, and I actually learned about hydration thanks to IGLUNA. So I'd say, yes, it definitely fostered collaboration between our two laboratories. And well, for Tokyo, I don't know if you've done through IGLUNA, but maybe you can tell us a bit more about that.
Oh, okay, so I'm Shinjiro from Tokyo. So I didn't know about the competition or the IGLUNA, but yeah, I came to the MIT and happened to meet some of the guys at MIT and introduced the competition, which as a aerospace student, it sounds very interesting to me, so I joined.
Yeah, related to that, I have a question. Somebody saying that a really great presentation, but how can we join the project? Somebody's asking that.
Our email is on the slides, so drop us an email.
Yeah, please come join us. Yeah. We're an international team, so it almost doesn't matter where you are.
Mm-hmm. As long as you have a Zoom account.
So, and this year, what has been the most difficult obstacle to develop your project?
I can answer part of that from the analog side of the project. The lack of access to the rig and to be able to build has not stopped us in our tracks, but certainly slowed us down a lot. I've literally gone into our warp room and taken pieces off of the rig and brought them home with me to continue working on them. I've had handoffs of various team members where, we'll drive to each other's house and, put the thing down on somebody's stoop and walk away so that it's safe for them to pick it up. So that's slowed us down with the drill, with the deployment of the tachometer, which we have actually done. The EPFL team did a fantastic job of developing that, boxed it up in this wonderful kit that came with absolutely everything except dinner. And, we were able to very quickly deploy it and test it and do things like that. But we had to test it in my driveway on a concrete block rather than on a sample of regolith. And so there have been things like that that have certainly impeded progress, but not stopped it. On the digital side, I'll let other folks comment.
Maybe I can talk about the development of the tachometer. I would say that same as Roland, due to the restriction, due to the coronavirus, we really had to use homemade equipment and things like that because there were a lot of restrictions. So yeah, it was sometimes a little bit hard to test everything, but I guess we figured it out. So in the end, it's good.
Yeah, it was kind of a challenge. My apartment did turn into a laboratory, and I had to drill concrete on my balcony, but my neighbors didn't complain too much, so it's fine.
Yeah, my dining room table became a lab bench for a couple of months.
And if I can add something, we had excellent support from our universities. So, for example, the Department of Aeronautics and Astronautics at MIT gave us permission to order materials and equipment and have them delivered to to home addresses of students. And in this way, we could get around the difficulties and continue working. So there was good flexibility shown by everybody.
Yeah, we weren't going to be stopped.
Yeah.
And I would say the same about the especially the physics section at EPFL, who's been very compliant and who just brought us even though there were some restriction, who were just find ways to find what we needed to do the several experiments we did with the sensor.
Okay, maybe also a bit related to that. Somebody's asking related to the major risk of your project. Of course, you probably did not expect the COVID situation risk in your risk plan. Did you perform the risk mitigation in the duration of the project, or how did you perform that?
We certainly didn't anticipate a COVID level of risk, in that we didn't anticipate everything being shut down. We had risk mitigations for a lot of different parts of the project. if equipment got delayed or missing, if equipment failed, things like that. I think the COVID risk mitigation, we've been, working well as a team to figure out how to do that, and working well as a team to figure out how we keep moving forward in spite of, issues like we can't get in and work on the rig, or, we have to get components sent home, or things like that. I'll let others speak as well, but I think we've done an outstanding job given where we are. We do have limited access to MIT, and we have a policy for working on anything physical that there has to be 2 people present, so that if there's an injury, there's somebody to handle it. So fortunately in Massachusetts, we're actually in the part of the US where cases are declining. And so having 2 people in the room is probably, with masks and gloves and safety equipment, is probably a reasonable thing to do.
But it wasn't until very recently. So I think that was one big reason why we couldn't be at the lab and together.
Right. I can add a few words on the systems engineering side of risk mitigation. So there were 2 major branches here. One is because this is the 3rd year now for this project, we have at the subsystem level identified all the sources of risk, and we had 3 major areas of improvement. The first was the mechanical interface between the drill and the drill bit, that you saw the work that was done, that Roland presented. The second was the upgrading of the quality of all the electronics and the complete redesign and the rebuild of the electronics panel, which we didn't talk about in this presentation. We didn't have time to talk about everything. But because this project is being done on a relatively small budget, we have to pick our battles every year. And in this 3rd year, we are using our money to improve the quality of the electronics. So that mitigates a second source of subsystem risk. And then the third is the fact that we have used all the systems that worked. We deliberately designed it to keep everything that worked well. So everything that was proven in competition conditions was kept. That includes the drill bit, the structure and the stepper motors and so forth. So all of this was the risk mitigation at the upfront design subsystem level. The biggest part of risk mitigation hasn't happened yet. This is at the system level, and we cannot start that until we start on the integrated testing, integration and testing. And for this reason, the program for this year had a lot of time set aside to actually put our rig on top of the icebox and keep testing. We even worked on, before the COVID emergency, we worked on setting up a freezer with a coolant loop to keep our ice frozen for months at a time, so that we could load the 400 kilos of ice in the box once and then keep it for a few months. But all of this is for the future now. We don't know when. We are not in control. The public health conditions are in control. But once we are able to, most of the risk mitigation at the system level will happen when we are going through integration and testing.
Thank you very much, Roland. I have probably a last question. Somebody is asking, what TRL did you reach with your system? Just for explaining, the TRL is a technology readiness level ranging from 1 to 9, 1 being a basic principle observed, and 9 really the system is proven in the operational environment. In your case, in a space, for a space system, of course, in space.
I can take that question. So this system, the highest we've reached with the hydration system, it was about a year ago when we reached TRL4. But right now, because of the extensive changes, we're back down to TRL3. And we hope to get back to TRL4 once we complete integrated testing. But because we have not done any realistic environment, then we would not pass above TRL4 until we have a lot more funding to test in a more realistic environment.
So I think there is no other question. So thank you again, Hydration, for this fantastic presentation, and to everybody for the interesting Q&A session. And as we heard, water is, of course, an extremely important, even vital resource on Earth, but also in space, as well for life as for technological applications like fuel for rocket engines, for example. Your project is thus really of utmost interest. So we really appreciate your hard work and wish you all the best for your next steps. With this, I want to conclude the session. So please stay tuned for the next show, P4VGELM product show, coming up tomorrow morning at 11 o'clock. For all of you watching through YouTube, please fill in the survey in the video description below. Your answers are very valuable to get to know you better for our future events. Thank you and see you soon. Bye-bye.
Thank you. Bye-bye.